Thank you very much. My second talk will start with a review of the first talk. So I just want to recall you the main facts, because I was told that I was a little bit too fast, and I apologize for this, so I will try to be a bit slower. And I start, as said, with the first talk, with the main facts of the first talk, so the review. So what is important? The first important object I introduced were Sturmian sequences. Sturmian sequences are defined combinatorially. So they are defined by the requirement that the number of blocks or subwords of length n is given by n plus 1. So these are the easiest, if you want, the easiest sequences on two letters that are non-periodic. These are Sturmian words. This is a combinatorial definition. Here we have a dynamic definition of seemingly different sequences, so-called natural codings of rotations. So I define a rotation on the unit interval. So T is the unit interval with its endpoints glued together. So you get a circle, but you want to imagine this as a unit interval with endpoints glued together. And here you define just a translation, which becomes a rotation on the circle by a vector alpha. I want alpha to be irrational, otherwise it becomes periodic, and this is a case I'm not interested in. So now this rotation can be regarded as what is called a two-interval exchange. So if you subdivide your unit interval in the intervals I1 and I2, then under this rotation, all the elements of this interval are shifted by alpha, and all the intervals contained in this interval are shifted back by 1 minus alpha. So the rotation exchanges those two intervals. Now, what is a natural coding of such a rotation? So you start with some point x on the torus, on the glued unit interval, and you hit it with the rotation. Then you get x, x plus alpha, x plus 2 alpha, x plus 3 alpha, and always you make sure that your values are taken modulo 1. So you get a lot of points, and you keep track of in which of these two intervals your points land. Whenever you land in 1, in the interval I1, you write out the letter 1. And whenever your orbit lands in the interval I2, you write out 2. And if you go on and keep going forever, this will produce you an infinite word on the two letters 1 and 2. So at first glance, those two have in common that they are both words, or sequences, right infinite sequences over two letters. And the nice thing is that one can show that those two are the same. So they produce the same set of sequences. This is the theorem of Morse and Hedlund. So I put it here again. You can formulate it for sequences, or you can formulate it for whole dynamical systems. So a sequence is Sturmian if and only if there is an irrational number between 0 and 1 without loss of generality, such that the word is a coding, natural coding for this rotation. So natural codings and of rotations and Sturmian sequences are just the same. Now, as I told you yesterday, you can produce dynamical systems starting from Sturmian sequences. You take a Sturmian sequence and you look at the shift orbit of the Sturmian sequences. So you just chop off the first letter. Then you get a lot of words. You get a whole sequence of words, the shift orbit. You take the closure of this shift orbit, call it x sigma. Then this shift orbit together with the shift forms a dynamical system, a topological dynamical system, and it turns out that this topological dynamical system is measurably conjugate to an irrational rotation. Okay? This is for words, this is for sequences. Both theorems say that two objects are the same or essentially the same. Measurable conjugate means that the conjugacy is a measurable function. You cannot expect this to be a continuous function because X sigma and the torus have different topological structures. Okay? This is a central theorem. So the interesting thing is that when you prove this theorem, some other important objects come up, namely classical continued fraction algorithms. So we have three things. We have combinatorics, we have dynamics, and we have arithmetic. So the arithmetic, so to say, builds the bridge between combinatorics and arithmetic. This is very beautiful. And what I want to do, I want to generalize this. So here we have words over two letters and codings of rotations on one-dimensional tori. My aim in the next lectures is to go to more letters. I want to look at words that are on the alphabets of several letters, of D letters, for D some integer greater or equal to 2. And I would like to prove that under certain conditions, the analogously defined dynamical systems are conjugate to irrational rotations on higher dimensional tori. Okay? This is my aim. And on the way again, arithmetics will come up. So all this turns out to be related to higher dimensional analogues of continued fraction algorithms. So let's go back to the theorem of Morse and Hedlund. I talked about the proof. I just want to give you the highlights so that you see the basic idea and why continued fractions show up. So what we want to do, we want to show that both Sturmian sequences as well as rotations are S-adic. S-adic just means that they are generated by a sequence of substitutions. So Sturmian sequences as well as rotations can be written essentially in this way, essentially meaning that there may be some shifts on the way, but we don't bother with this for the moment. So we are on the level of systems and not on the level of sequences. You could put it like that if you want. We're just interested in these guys, or the language of these guys. Anyway, essentially, Sturmian sequences as well as rotation sequences can be written in this way, where these sigma are the Sturmian substitutions, so very easy substitutions. And it turns out that the structure of these substitutions is related to the continued fraction algorithm. So why are they both S-adic? Sturmian sequences are S-adic since they are balanced. It's not trivial to prove that they are balanced, and even if you know that they are balanced, you have to work a little bit to show that this entails that they are S-adic. But for the moment, this remark is enough. More interesting is the proof why natural codings of rotations are S-adic. This is proved by what is called induction. So you look at the rotation on the interval 0, 1, and then you zoom in. You look at a smaller subinterval of the interval 0, 1, and you wait until your rotation turns up in this subinterval. Okay? So once in a while, you hit this subinterval. The rotation is irrational, so the orbit is dense. It is clear you will get there now and then. And the interesting thing is, even what you get when you just look into the subinterval and you keep track of what the rotation does there, it turns out the rotation induces a rotation on this smaller subinterval again. And with the smaller rotation, you do the same. You induce an even smaller and smaller interval. And to get the intervals at the same size, after each step, you stretch them. So you renormalize so that you can see the rotation always at the same scale. So just once again, the picture. We start with 0. And just for technical reasons, we don't perform our rotation on the interval 0, 1. We perform it on the interval from -1 to alpha. We rotate by alpha. So 0 becomes alpha. It's glued, so alpha is the same as -1. -1 becomes -1 plus alpha, and so on and so on. And eventually, you end up at -1 plus alpha times floor of 1 minus alpha. This is the last point in the orbit of alpha that is less than 0. In the next step, you enter the interval 0 alpha. This point is important for us. We induce on this interval. So we look what our rotation does on this interval. So for instance, 0 comes back to here. The next step, it goes here. Then it again goes here. The next step, it comes somewhere here. And you get a new rotation induced here. You stretch out. So here is your new rotation. Now 0 is mapped to this point. Before 0 was mapped to this point. So you get two rotations. And what you find is that the natural codings of those two rotations, two infinite words, they are related to each other by substitution. So this word here is a desubstitution of this word. Or put it in the other direction, if you substitute this word, you end up in this word. The important thing is, this word here can be written as another word hit by the substitution. Okay? So this word u is sigma 1, here it's sigma 1, whatever, I don't care, it's sigma 1 of this word. And now you can iterate. So the word becomes sigma 1 times sigma 2 of another word, if you induce again. And you induce again and again and again, and this is how you produce your sequence of substitutions. So Sturmian sequences are S-adic, and rotations are S-adic. That's why they are the same. And it's not hard to do the transition from words to sequences. So I want to generalize this, and in the course of the generalization, this picture will be of importance. So I want to explain this picture again. You have a Sturmian sequence. A Sturmian sequence is just a sequence of 1s and 2s. I want to represent this sequence geometrically. Whenever a letter 2 occurs, so I start at the origin. Whenever a letter 2 occurs, I go up. Whenever a letter 1 occurs, I go to the right. So 2, 1, 1, 2, 1, 1, 2, 1, 2, 1, 1. Since the Sturmian sequence is balanced, it turns out that it remains very close to some direction. This direction, I call it the generalized right eigenvector, but whatever. This direction is related to the frequencies of the letters 1 and 2 in the Sturmian sequences. So if you have lots of 1s and only very few 2s, your slope will be somewhere here. And the more 2s you have in a word, the steeper your slope will become, right? So this is a broken line that codes the Sturmian sequence. And now I want to visualize why a Sturmian sequence is related to a rotation. So if you look at the points of the Sturmian sequence and project them down parallel to the line which is approximated by the Sturmian sequence, then we project on an orthogonal space. So what happens here? First point is projected to the origin. If you go up, the next point is projected somewhat upwards. If you go right, the next point is projected somewhat downwards. And if you inspect this a bit more closely, you find out that each step in the Sturmian sequence does a rotation here. So from the origin you go up, then you go back down, you go back down, you go up, and this exactly does the rotation on those two, on this, let's say first on this big interval. So this is the conjugacy of the dynamical systems. So here you have your combinatorics, and this combinatorics by the shift has a dynamics, and this dynamics induces by way of the projection a dynamics here, which turns out to be the rotation by alpha. Okay. So I wrote here two intervals. So if you are in this interval, then your rotation shifts you down. If you are in this interval, your rotation shifts you up. So as I said before, a rotation is an exchange of two intervals. Okay? So everything is nice and good here. These are intervals. They are, I should say this, so you project down. Of course, if you project down, you get a countable set. You take the closure, and since the slope here is irrational, it turns out that this closure becomes an interval. So you have something of positive measure, which is important. The second important thing is that the light interval, which projects the points that come up after you read 2, and the dark interval, which comes up, wait, is it true what I'm saying here? the dark interval comes up before you read 2 and the light interval comes up before you read 1. It is nice that those two intervals are separated. They only have the origin in common. If they would have overlaps, our rotation would be spoiled, right? So this is the first important thing, which is not hard here, but it's important, of course. The second important thing is, this is an interval, and we can do what we did before. We can glue the endpoints of the interval. So our interval exchange really becomes a rotation on the glued interval, okay? All this sounds easy for intervals, but it turns out when we make the transition and go to higher dimensions, instead of intervals, we will get fractal sets, and it is not at all clear in general that these fractal sets have nice properties to change subsets, subintervals, to get a domain exchange instead of an interval exchange, and it is also not clear how to glue them in order to make this domain exchange rotation. These fractals are called Rosi fractals. So imagine if you have a word with 3 letters. You also can associate a broken line, but you need 3 directions. So you get some broken line in Euclidean 3 space, say. If everything is nice and neat, then it will be a good approximation of some direction. And then you can project down, and you will get some object in the hyperplane, which is a plane if we deal with 3 letters. And it turns out that this image cannot be something nice. It has to be a fractal because it is related to Markov partitions, and Markov partitions in higher dimensions have to be nasty by some old result of Bowen. So we get fractals, and we have to play our game on fractals, and this will be one of the challenges that we will face when we go up to higher dimensions, okay? So essentially, I will do exactly the same again when I talk about the higher dimensions. But it's not so trivial. So on the way, there are some obstacles we have to master, okay? So these intervals, they are special examples of what is called Rosi fractal. The reason why they are called Rosi fractal is that a mathematician from Marseille, a very famous one, Jörg Rauzy, he was the first one who studied this for more letters, for 3 letters. He came up with a very interesting and appealing example, which had a lot of impact and created the first fractal, which is now called Rosi fractal. So the next thing I was talking about yesterday was bijectivity. So if you remember, we had the continued fraction algorithm, and if you do one step in the continued fraction algorithm, then you lose one integer that makes up the continued fraction expansion, and you cannot go back. So we want to make everything bijective, and we do this by looking at the induction process. The problem with injectivity comes from the fact that we lose information. We lose information because we just throw away part of the interval. And the idea, and this goes back to a paper by Pierre Arnoux and Albert Fischer, the idea is just to restack the intervals. And it turns out restacking the intervals in this way is not enough, but you already can see a nice box here. So instead of working with intervals, one works with boxes. So what we do is, we have on the bottom, we just have what we had before. One interval is of length 1, so here is -1, here is 0, here is alpha. And we throw away those 2 intervals. But in this case, we don't throw away intervals because we have another coordinate. So we can play also in the y coordinate. Instead of throwing away those 2 intervals and looking at the induced rotation here, we take those boxes and just pile them up on the smaller box. So here is a large box, here is a small box. The heights of the boxes are chosen in a way that the total area of this L-shaped region is equal to 1, and that the wider box is also the higher one. So what we do is we take those 2 boxes, pile them up. It's the same as here. We just don't want to forget this. We just pile it up. But we don't want to have only integer heights here. We want to have real numbers as heights. Okay, we just add 1 dimension, which is often done when producing natural extensions. So to make our process bijective, we don't throw away boxes, we just restack them. And now we do the same as we did before with the intervals. If you keep on restacking, you get something which is very thin and very high. We don't like this. That's why we just renormalize, so that we always see what is going on. Okay? So at the end, what you get is you get another pair of boxes. I put away these lines here. We don't need them, but they would just go here and here. We renormalize. So in total, from an L-shaped region, we produced another L-shaped region. And of course, you can go backwards. Yeah? You can go backwards. You just cut this horizontally, and what do? You cut this horizontally and put it here. Then you go back again. So, but this mapping on L-shaped regions is a bijective mapping. A priori, it is a mapping on 4 parameters, the heights and the lengths of the rectangles, but we have 2 conditions. One of the baselines is equal to 1, and the area is also equal to 1. So we can eliminate 2 of these 4 parameters, and we get a mapping of 2 parameters. So if you see this, if you see the procedure, you can just calculate what this mapping does. The first coordinate you know, and the first coordinate, so this and this, so this length is alpha, and this length is just the Gauss map of alpha. The second coordinate just follows by calculation, and at the end you get on suitable subspaces, which I don't want to talk about, you get this nice thing here. So you found a geometric way to produce what is called the natural extension of the continued fraction map. Okay? Natural extension of the continued fraction map. There are several natural extensions of the continuous fraction map. This is one of those. Another one goes back to Japanese people, to Ito, Nakada, and Tanaka. It has the nice property that it acts on squares. This one doesn't act on squares, so you have, I don't want to go into this. These are other regions, also quite natural ones. Good, so this is called the natural extension of the Gauss map. Also, this game you can play for several letters, but I will not do it. And another very nice thing is that these L-shaped regions, they can be just piled up in a way that they tile the plane. And on this tiling, you can see the Sturmian sequences, the original Sturmian sequences. So if you mark some point, some arbitrary point, then you can go up and you can go to the right. And for instance, when you go up, you hit horizontal lines. Whenever you hit a horizontal line that belongs to a large rectangle, you write out 1. Whenever you hit, which you cannot see here, but here you would hit a small rectangle. Is it true? Yeah. Whenever you hit a small rectangle, you write out 2. And by way of this, you produce a Sturmian word that has the same language, regardless of the point where you are. So all the x coordinates here parameterize Sturmian words with a given language. Okay? You can do the same here. You can go horizontally, and again, whenever you hit a vertical line, you write out 1 or 2, depending on whether you enter a small rectangle or a large rectangle. This gives you another Sturmian word. Okay? Now, we can recode the Sturmian word. We can desubstitute it. When we desubstitute it, we lose the first substitution, which is not bijective. And it turns out that this procedure here makes everything bijective. If you do one step in the induction, one restacking process, your fundamental region looks like that. We don't renormalize here, we just do the restacking. You see that the rectangles that are restacked here, they are indicated by the dashed lines. So you take this rectangle, and you just pile them up here, and what you get is this fundamental region. And now you can do the same I did before with this modified fundamental region. Again, if you go up, you produce a Sturmian word, and if you go to the right, you produce a Sturmian word. Since these rectangles here are thinner and longer, if you go up, you hit horizontal lines not so often as before. So you lost something, you desubstituted, But this is made up for when you go right, you win something, because the rectangles became thinner, you hit boundaries more often, and so this is substituted. This is desubstituted by a substitution. This is substituted. So you don't lose the substitution. This mapping from pairs of Sturmian words to pairs of Sturmian words is bijective, contrary to the map defined by the coding process, the desubstitution, where you lost something. So again, we made something bijective. And now, so before I come to this, I want to show you a video. So the nice thing is, so in this paper by Pierre Arnoux and Albert Fischer, many bridges are built between seemingly different areas. And a very, very nice thing, I don't want to go into this very much, a very nice thing is that all this is related to geodesic flows. So when you do the renormalization process, you can do it smoothly and then make your piles. And it turns out that this smooth renormalization process can be regarded as a geodesic flow on homogeneous space being the space of lattices, in this case the space of two-dimensional lattices of unit fundamental mesh area. So this is very nice, and I show you something I was told I should call a trailer. So this is a trailer for a full movie that you will see, I think, tomorrow. And the movies I show you, they are due to Edmund Harris, who will do the presentation tomorrow. So I now need to do something. I need to change to web browser. And here you see the restacking, no, renormalizing, restacking, renormalizing, restacking, renormalizing, restacking, renormalizing. So you see this process goes on forever. Whenever you restack, you do one step in the continued fraction algorithm, actually even in the natural extension of the continued fraction algorithm, and in between you have your flow. So this is a suspension flow of the continued fraction algorithm, and the very nice thing is that this is not just some flow, this is a very important flow. This is the geodesic flow on hyperbolic space. Whatever that is, so I don't want to go into this, I just want to show you some other pictures. Wait, I need to wait for the good moment to switch. Where is the good moment? Takes a long time. Now, here it is again, but now you see that if you wouldn't renormalize, you would get a lot of small rectangles. This is the restacking process again. Okay? So Edmund Harris is a real master in doing visualization of mathematics, so I strongly recommend you don't skip his talk. So this is certainly something worth looking at, and he will show you lots of other pictures and movies. So far so good. I go back to the slides again. And start with the second part. So now, as I told you, I want to generalize everything to higher dimensions. And so before I start doing this, I will show you the limitations that we have to face when we go for higher dimensions. So unfortunately, the theory is not so complete as in 2D case. So there are counterexamples. There are S-adic sequences that are proven to be not codings of rotations on the torus. I will start with this. Problems with generalizations to higher dimensions. And after that, I will start from the very beginning. So you can, if you want, forget everything I said before. I will set up from scratch the general theory of S-adic sequences and generalized continued fractions. And then I will step by step show you some properties of these sequences that can be turned into properties of the underlying dynamical systems. And finally, we will have a set of properties that will turn out to be sufficient to get our rotation. So each of these properties, if you want, will entail that the Rosi fractals that we produce by our broken lines have certain properties. So we make our Rosi fractals nicer and nicer until they are so nice that they admit the interval exchange, which is now a domain exchange, and until they can be glued together to make up a fundamental domain on a torus, where this domain exchange actually becomes a rotation. So once again, we do the same again. So it's the same program, but there are some obstacles on the way. So as yesterday, I want to stress on some papers that are useful and related. So the problems that come up in higher dimensions were first observed by Jörg Cassaigne, who is here, and his co-authors, Sebastian Ferenczi and Luca Zamboni. They showed that the direct generalization of this Sturmian rotation stuff is not always possible. This is 17 years old. If you want to look for the survey on S-adic expansions, I recommend you the survey by Valérie Berthet and Vincent Delacroix. And the theory I'm developing here on the higher dimensional generalization of this correspondence between S-adic sequences, generalized continuous fractions and rotations, then you will find this in this paper. And you also find all this, of course, in the lecture notes that I provided. So today's talk will be concerned with sections 3, 4, and 5. I don't know how far I will get, so somewhere in that range, okay? So let's start with the first example I was already talking about, which goes back to Jörg Rauzy, to 1982. So he came up with one single substitution. And he looks at what is called the fixed point of this substitution. I already talked about such a fixed point yesterday. So 1 is equal to 1. If you don't hit it with the substitution, you get 1. If you hit it with the substitution once, 1 goes to 1, 2. And in the next step, you hit these letters with the substitution separately. So 1 goes to 1, 2, and 2 goes to 1, 3. So you get 1, 2, 1, 3. And what you see here, since 1 starts with 1, the 1, 2 is maintained here, so nothing changes. It just gets longer and longer if you hit the word with the substitution. Here is the next step, the next step, the next step. Eventually this becomes an infinite word. The limit is to be taken with respect to a topology on sequences. So this is a slight abuse of languages. So this is not an infinite word here. So if you want to be really precise, you should write here an infinite block of ones, but this is just not so important. You saw that since everything remains constant when iterating, remains constant at the beginning, that you get some infinite word here. Infinite word on 3 letters. You look at the shifts of this word, so you chop off the first letter and look at the set of words you get. So you get the orbit of this word under the shift and you close. So you get a set X depending on a constant sequence of substitutions. You always do sigma, 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 no sigma 1, sigma 2 here. That's why I wrote it like this. Together with the shift, this forms a dynamical system, and this is often called a substitutive dynamical system, contrary to the S-adic dynamical systems, which are more general because you can deal with sequences of substitutions. So here you always have the same substitution as we had yesterday in my example with the Fibonacci-like substitution. So we look at this dynamical system, and the interesting thing is that Rosi in 1982 was able to prove that this dynamical system is conjugate to a rotation on the 2-dimensional torus. So 2-dimensional torus, what do? You have a square of paper, if you want, then you glue the opposite sides, and you get a cylinder, then you glue the opposite sides of the cylinder again, and you get a donut. Okay, this is the 2 torus. You can do this also in 3D, but it's no longer so easy to visualize. If you are in a 3 torus, the best way to visualize a 3 torus is so you think you are standing inside the 3 torus. So if you are standing inside the 3 torus, if you look ahead, you will see your own back. Okay? If you look back, you will see your face. If you look left, you will see again your right side. Your shoes will be up there again, and your head will be down. This is the 3 torus. You can do it in all dimensions, of course. 2 torus is donut. This is easy to visualize. So, he proved this. And the funny thing is that the analog of the intervals and the subdivision of the intervals is now this nice figure, which is called the classical Rosi fractal nowadays. I told you that the rotation comes by way of an interval exchange and then gluing. So here we need to change domains. And I mean, for intervals, it's not so hard. If you have two intervals and if you switch them, you get an interval again, right? But if you switch these strange guys, it's not so clear that you get the same guy again, but it is true. So if you take this piece, put it here. You see this boundary here is the same as this boundary. You can put this piece here. You can put this piece up here. And you can put this piece here. And you will get exactly the same figure. I will show you this later. And it's even better. So this guy here can be used to tessellate. And now the tilings come up because the school is about tilings, and this is important here. So this shape can be used to tessellate the plane, if you take the right affine transformation, to tessellate the plane by the lattice Z2. Okay? So this is a tiling by way of a lattice. And of course you can project this on a torus. And a tiling with respect to a lattice is a fundamental domain of a torus. So this covers a donut. If you just glue it together, it fits together. And I wanted to make this picture, but I had no time. I want to see a Rosi fractal on a donut, so it really perfectly fits together. Probably I should ask Edmund Harris to do this if he didn't already do. So this is the main tool of the fractal. How does this fractal emerge? How does it come up? Remember the broken line. You start at the origin, 1, 2, 3. Let's see, 1, 2, 1, 3. You go on this word, you get a broken line that is nice. It turns out to produce a balanced word, which is reflected by the fact that it approximates some vector very well. So you can project down the vertices of the broken line, and you get a compact figure. You get this guy here. The colors come from the fact at which point you project. If you project before reading 1, before reading 2, or before reading 3, you use different colors. And now it's the nice thing that explains a little bit the domain exchange. You can write out a light point before reading 1 or after reading 1. Depending on this, you get this guy or the guy with exchanged domains. We'll come back to this later, probably tomorrow. So now I come to something important. So in 1991, Pierre Arnoux and Jörg Rauzy, they generalized the Sturmian setting in the most natural way and proved a lot of important results. So do I need this? Oh, why not? So in the following definition, a right special factor of a sequence. So now we have 3 letters instead of 2. We go for 1 letter more. Is a subword of the sequence with the property that there are 2 distinct letters such that we can concatenate the word with both of them. And both of these concatenations again occur in W. Okay? So if you have a block of length n, you can prolong it 2 different ways. And now it comes the definition of what is now called an Arnoux-Rauzy sequence, 1991. A sequence is called an Arnoux-Rauzy sequence if it is a 3-letter sequence. The complexity function now is 2n plus 1. And we require that W has only 1 right special factor and only 1 left special factor. So left special factor is of course defined just analogously on the other side for each given length n. It is rather easy to see that if there is only 1 right special factor, then you can use even 3 letters to prolong it. This has the effect that the so-called Rosi graph becomes nicer, and you can find the sequence of substitutions to encode this in an S-adic way. I should mention that there is a brand new class of sequences that goes back to Jörg Cassaigne that was invented just 2 years ago, which has even nicer properties than this one, and the study of the theory of this class of sequences is on the way now. We want to confine ourselves to these sequences. So 1 right special factor entails that this Rauzy graph becomes nice. And so the hope was that these sequences behave like the Sturmian sequences. In particular, they code rotations on the 2 torus. So 2 letters, 1 torus, 3 letters, 2 torus, right? This drop down comes from the projection. You lose 1 dimension. So you have broken lines in d dimensions, so in 3 dimensions, but your rotation takes place 1 dimension lower. So this is the hope, and unfortunately this is not true in general. This was proved by Cassaigne, Ferenczi and Zamboni in the year 2000. They worked on this sequence and they went even farther. I will show you later. But first of all, a positive result that is also contained in this 1991 paper. Again, we can recode these Arnoux sequences by substitutions. Instead of 2 substitutions, we get 3 substitutions. But if you look at them, this is a very nice analogy. If you just cut out this piece here, you see the Sturmian sequences again, right? This is just 3D Sturmian sequences. Okay, so it's cooked up in a way that it's as close as possible to the Sturmian case. And the first nice result is that completely analogous to what we had in the 2-letter case. So Arnoux sequences is up to shifts. A sequence like that. You just replace the Sturmian sequences by the Arnoux sequences here. Okay? And, I mean, if you want to be more precise, then you say that Arnoux sequence has the same language as this guy. So again, you have to put shifts, which I don't want to do here. This is another example of an S-adic system, and of course you can define the orbit closure of, sorry, now U becomes W, I'm sorry for that. So you can define the orbit closure of an Arnoux word in the same way as you did for Sturmian words. You can define a dynamical system by combining it with the shift, and this is an example of an S-adic system, like the Sturmian systems are. Okay? So as you see here, you don't have a single substitution that you iterate, but you have a whole set of 3 substitutions in this case, and you can form arbitrary sequences with these substitutions. Okay? This dynamic system has a lot of nice properties. The first thing is terminology. So again, an Arnoux sequence is defined in terms of a sequence of substitutions. I should say a system, but let me be a bit sloppy here. So essentially, a word is defined by a sequence, and we call this the directive sequence of the word. Okay? So you have an Arnoux word, and you have an associated sequence of substitutions. This is the directive sequence. So now, it turns out that, what did I do here? This is not totally true, what I wrote here. Wait. No, it's okay. So you look at the sequence of incidence matrices, of Abelianizations. This gives you a sequence of matrices. Okay? You have the sequence of substitutions, and you look at the incidence matrices. You get an Abelianized sequence of matrices. And if for each index m, there is a larger index n, such that this product of the block is positive, then we say that this sequence of matrices is primitive. So you find positive blocks infinitely often, okay? And it turns out that these positive blocks entail minimality of the system. This is not so hard to prove, but I don't want to comment on this. So we have minimality, which is a nice property. We have another nice property that can be derived from a result due to Boschernitsan. I think it is 1985 or something like that. It's an older result. This says that if a word has linear complexity function, then the associated symbolic dynamical system, here the associated S-adic system, is uniquely ergodic. So we have two.
For 2n plus 1, 3n plus 1.
Oh, linear, sorry. Did I?
2 is because of the 2.
So linear complexity is not enough?
No, because you have interval exchange with.
Yeah, 2. Sorry. Yeah. We need complexity 2n plus 1. Okay? Yeah, sorry, this is wrong. Thank you. So since we are in 2n plus 1 complexity case, this is uniquely ergodic. And also interesting, so in this paper by Arnoux and Rauzy, it is shown that you can code these sequences by exchanges of 6 intervals. So instead of 2 intervals, you take 6 intervals, and you code, and you can cook up Arnoux-Rauzy sequences. But what we want is, we want natural codings of torus rotations. So now, if you define this Rosi fractal, so what did you do? You cooked up the broken line, and then you project it down, and you got a compact set. And on this compact set, you could work. The reason why you get a compact set is that this sequence is balanced in this sense. So it's similar as for 2 letters. This is just a little bit more general. So you take an integer c, and we say that the sequence of 3 letters, the same is for d letters, but I am in the 3-letter case here. A sequence of 3 letters is c-balanced if for each pair of subwords of the same length, the number of occurrences of a given letter A is almost the same, save for this constant c, which is an absolute constant not depending on n. If you have 2 factors, each letter occurs roughly same number of times. Okay? And this property entails that your Rosi fractal is compact. Okay? This is equivalent, you can prove. And now, so by a very clever combinatorial argument, in the paper by these 3 guys in the year 2000, it was shown that Arnoux sequences can be bad guys. So they are not always balanced. So you can find an Arnoux word which is not balanced for whatever C you choose. So if you have your favorite direction, whatever you take, your broken line will just go farther and farther away. So if you project down, there is no hope to get a compact set. So this doesn't say that our words are not conjugate to rotations for now, but at least it says that we cannot get our conjugacy in the way we would like to, in the way we are used to in the Sturmian case, right? So another step is needed to really exclude that this can possibly be the case. This balance unbalance just entails that the diameter of the Rosi fractal is not bounded. So we have a different situation. It could also be interesting to study these guys. I don't know what kinds of properties they have, or if they can be visualized at all. Probably it's not so easy because it takes quite a while until you get away from your favorite line. Far enough. So whatever. Here's the theorem. So Cassaigne, Ferenczi, and Zamboni were really able to prove not only that by way of the standard construction you cannot get the torus rotation, but it's impossible to get the torus rotation. And once again, Gérard Rosi enters the game. He proved the result, saying essentially that torus rotations, they are related to something which is called a bounded remainder set. So if you have a rotation, then you can define sets that are hit by the rotation as often as they should be hit according to the measure of the set. So a small set is hit rarely, a large set is hit more often, but bounded remainder set means it is hit as often as it should be hit according to its measure, apart from a finite number of times, uniformly bounded number of times. This uniform bound is related to the balance somehow. So by using this result, here's the definition of a bounded remainder set. You don't need the details. By using this result, the authors were able to show that it is impossible to construct a torus rotation that is conjugate to the given Arnoux-Rauzy system. So the reason is that this lack of C-balance prevents us from getting what is called a bounded remainder set, and so we cannot possibly get a torus rotation for these words. So this is bad news, because this says that we cannot generalize the theory without some additional assumptions on our sequences. It turns out that in this construction, you need large blocks of substitutions of the same kind. So there are 3 substitutions and say sigma 1 has to come up very, very often. If you interpret this in terms of continued fractions, this means that in the continued fraction algorithm, and there is a continued fraction algorithm related to Arnoux and Rauzy sequences, that you have large blocks of large partial denominators. Okay? This is something we don't want. If we get this, the things behave strange, and we need to exclude this. Okay? This is one of the things we have to be careful about when we want to come up with a general theory. So now they went even further. So there are some dynamical properties that are shared by rotations, by minimal rotations. So minimal rotations have a lot of eigenvalues, whatever that is. And what Cassaigne, Ferenczi, and this time together with Messaoudi, I think, proved in 2008, is that Arnoux-Rauzy sequences are very bad. They are, talking about spectrum, they are on the completely other side of dynamical systems. So rotations have a lot of eigenvalues, eigenfunctions, and some Arnoux-Rauzy systems, they don't have any eigenvalue apart from the trivial one, which is equal to 1, which is always there with constant eigenfunctions. So in other words, they prove that the transformation is what is called weakly mixing. So weakly mixing means that this thing goes to 0. Weakly mixing means that 1 is the only measure of eigenvalue, whatever that means. But there is a nice explanation of this, which I found in a book by Haimosh. So he talked about some notions of ergodic theory, and he explains them in a very nice way. So you have a glass, and you put 90% gin and 10% vermouth in it. So I did do it exactly the way that Haimosh did it. You can do it with milk and whatever, but so he did it like that, whatever. 90% gin, 10% vermouth in a glass, and so let V be the original region of the vermouth. So the glass is standing here, nobody touches it, there is vermouth and there is gin. Vermouth is in the region V. And then you take, so a given region in the glass, okay? Then you see that, so take the H measure, or the not H measure, the Lebesgue measure in the glass, call it mu. You see that this guy here is the amount of vermouth that is in F after you used your spoon n times to stir, okay? So your transformation T is just boop, okay? It's just stirring, okay? And so now there are 3 different kinds of spoons. There is the ergodic spoon. So if you stir with an ergodic spoon, what you get is that the amount of vermouth in this chosen region F is 10% on average, okay, when you go on spooning. Mixing, if you have a mixing spoon, this is the best one, then the amount of vermouth in F becomes very close to 10% after a while, and it stays very close to 10%, gets even closer and closer. And weakly mixing, this is the second best one, this is the one we are interested in, so the amount of vermouth in F is close to 10% after a while, apart from very few exceptions. Yeah, the few exceptions should be few enough to make this limit 10 to 0, so we can check that. That's what it is. So I like this because now I understand what mixing is. So we are weakly mixing. So if suppose your glass is a ball, and suppose your spoon just rotates, okay? Then you can easily see that very often the vermouth piece will not fall into F, so you cannot have the mixing property. So rotation and mixing, this is something different. Mixing smears around the things, and the rotation just rotates, and it doesn't smear around. So this is some explanation of this, and here is the result of Cassaigne, Ferenczi, and Messaoudi. So you take a Arnoux and Rauzy sequence, forget about the shifts again, and then you look at the sequence of indices such that you have 3 different substitutions in a row, okay? And if this sequence of indices, so if there are very, very rare cases, sloppily speaking, where the 3 substitutions occur in a row, then they are able to show that Arnoux and Rauzy sequences are weakly mixing. Okay, I think this is a very nice result. It's sort of unexpected. There are not even no rotations, but they are something totally different. However, these three people also did a positive result. So you know, whenever you have an eigenvalue, you have something like a rotation. And what they proved by building up what is called Rauchling towers and studying them in a very clever way, generalizing early results that go back to Host, I think, they could cook up this. No, they could show that there are non-trivial eigenvalues. So for some cases, so there exist some Arnoux sequences with non-trivial eigenvalues. Interpreting this in terms of rotations, there are some factors of the dynamical systems that are rotations. So the system itself may not be a rotation, but at least something hinting towards rotations is there. So this is a positive result that they found out by very, very tricky and sophisticated arguments in their paper. So not everything is lost, but still we need to be a bit careful when we set up our general theory. And I will do this now. And so now this is the last time where I can tell you I start now from the beginning. So if you didn't like or didn't pay attention or whatever, now you can start again. Now is the last chance to start again. I start from the very beginning to set up the general theory. Of course, I will refer to the standard classical case to motivate things and to explain things, but essentially this should be self-contained. So we want to generalize the Sturmian setting to dimension or number of letters d, where d is larger than 2, okay? d equal to 3 should be the guiding case, or our examples come from there. So what will we have to face? We have sequences generated by substitutions over a large alphabet. Instead of continued fraction algorithms, generalized continued fraction algorithms will come up as the Abelianizations of our more complicated words. Instead of intervals, we will see Rosi fractals. So intervals become fractals. Then what we want is we want to get our rotations. We want to get rotations on the torus of dimension d minus 1. So think of d equal to 3 if you want. And we want to relate flows again to our setting. So this is the wild chamber flow. It's not a flow in the strict sense, it's an RD minus 1 action. And the nice thing is this flow can be coded. So let's take d equal to 3. This flow can be coded, and we worked this out. I will not go into this, but I just want to mention it. We worked this out for the Brun case. The funny thing is, so your flow has 2 real parameters, and so we can split this flow, and for each real parameter, one version of Brun's algorithm takes care. So we code arithmetically and geometrically this Weyl chamber flow by 2 Brun algorithms. One Brun algorithm for the horizontal direction, the parameter space of the flow of the R2 action, and another one for the vertical direction. So instead of restacking boxes, we restack 2 times Rosi fractals. This is the ultimate goal, but I will not get that far. The main thing I want to do, at least to some extent, even here I don't know how far I will get, I would like to show you this correspondence between S-adic sequences and rotations on the 2 torus or on the d minus 1 torus. Okay? So we have to deal with new problems. Once again, I tell you, so if you kept in mind this Sturmian thing, this is the guideline. So we do the same again, but here are the problems that we have to deal with. So the first thing by the mentioned papers by Julien Cassaigne and his co-authors, there is no unconditional generalization possible because of these counterexamples. So we need to be a little bit careful. So I talked about generalized continued fraction algorithms. So the theory of generalized continued fraction algorithms is less complete than the theory of the classical continuous fraction algorithms. There's also no standard generalization. This has to do with the structure of certain groups of matrices. So we have several choices here. Yeah, this is related to this. So the lattices, the structure of the lattices becomes more complicated. And I also mentioned that the projections of these broken lines that we will cook up are no longer intervals, they are fractals, and we need to tame these fractals in a way that we can play our game there, can do our dynamics there. And about the wave chamber flow, I already talked. So let's start at the very beginning. I want to define all the objects I use from scratch, at least most of them. So what is a substitution? Let A be an alphabet. A substitution can be defined as a non-erasing endomorphism on the set of words. Non-erasing means that each letter goes to a non-empty word. What endomorphism means, it just means what I said before. Substitutions are defined when you give their images on letters. By concatenations, you can define them on words, and we already saw a couple of examples for substitutions. So to say, the mother of all substitutions is the Fibonacci substitution. 1 goes to 1, 2, 2 goes to 1. The Sturmian substitutions were examples of substitutions. Then the Fibonacci substitution, this is the one Rosi used to define his prototype of Rosi fractal. I recall the definition here. This is a substitution. Also, the 3 Arnoux Rauzy substitutions are examples of substitutions. Once again, you can extend the definition of substitutions even to write infinite sequences, again, in the natural way by concatenating. It turns out that the mapping sigma that is defined on AN by way of this is continuous with respect of the usual topology. What is the usual topology? The usual topology says that 2 sequences are close to each other if they have a large common prefix. Okay? So I want to define again also the abelianization. So substitutions are the non-abelian world. The incidence matrix are the abelian world because substitutions don't allow you to switch letters. If you just count letters, then the order of the letters is irrelevant. So we are given a substitution, sigma, on an alphabet, and its incidence matrix is an A times A matrix. This is the number of letters in the alphabet. And in the columns of these matrices, there are the abelianizations of the images of sigma. Okay?
Generalization go to n to the power d.
Where am I? Oh, thank you. Yes, this is wrong. D should be written here. So the abelianization function, what does it do? So it takes a word and turns the word into a vector, and here the D is missing. So the abelianization of a word is just a vector formed by the integers. First coordinate is the number of ones, second coordinate is the number of twos, and the dth coordinate is the number of these. Okay? And so the abelianization of the images of letters of a substitution defines this incidence matrix, and this is again wrong here. Again, the D is missing here and here, so we are in D-dimensional space. A word is mapped to a vector, and if you hit a word by the substitution, then in the abelianized version, this is the same as hitting a vector by the incidence matrix. Okay? So after the abelianization, the matrix, the substitution turns into a matrix. So this diagram is a commutative diagram, which is written out here again. If a word, you hit it with sigma, and then with the abelianization, you get it the same as if you hit the abelianized word with the incidence matrix. Okay? So we deal with certain classes of substitutions. What is important for us is unimodularity. So we want the determinant of the incidence matrix to be equal to 1. This has the consequence that the inverse of the matrix is again an integer matrix. This is important for us. Otherwise, you need to adjust by introducing some p-adic factors. Everything becomes more complicated, and there's no need for doing this because most of the continued fraction algorithms not all of them, of course, but most of them are unimodular, most of the known ones. Another important property is the so-called Piso property. So a substitution is called a Piso substitution if the characteristic polynomial of the incidence matrix is the minimal polynomial of a Piso number. So what is a Piso number? A Piso number is an algebraic number, which is even an algebraic integer. And it has the property that all the conjugates, so all the other roots of the minimal polynomial of this algebraic number are strictly less than 1. Okay? And the Piso number itself, I should say, is greater than 1. Yeah, it's a positive number. All conjugates are less than 1.
In absolute value.
Sorry?
In absolute value.
In absolute value. Yeah. So I probably make a picture not to confuse people. So Piso number, the conjugates of the Piso number is like this. So this is the unit circle. The Piso number beta is here, and the conjugates are strictly inside the unit circle. So the boundary of the unit circle is not allowed. If you permit numbers on the boundary of the unit circle, you get Salem numbers, and this little difference is actually a big difference in many regards. Piso numbers are the good guys, and Salem numbers are very bad from the dynamic footprint. So here is some notation. So the boldface sigma just denotes a sequence of substitutions, and the boldface M denotes the associated sequence of incidence matrices. You see I make a simplification in notation. Instead of M associated with sigma M, N I just write Mn, not to overcharge notation. And since we will often deal with blocks of substitutions, I don't want to write out the compositions. I just use this bracket notation here. Okay, so sigma M N is just the composition of sigma M up to sigma N minus 1. You see this is a round bracket. This is a, how to call it? Cornered bracket, I don't know, but you see it. So block of substitution is the same for blocks of matrices. And now you also saw this. I define S-adic words. S-adic words are words that can be desubstituted infinitely often. So we had to prove this for Sturmian words. Now we just assume it. We want to deal only with words that have the property of being able to be desubstituted as often as we wish, infinitely often. So we start with the sequence of substitutions. We assume, it's not necessary, but in this talk I want to assume that the set of substitutions we use to cook up a sequence is a finite set. The set is often called S. That's why we have the name S-adic. I think the name S-adic goes back to Sebastian Ferenczi, if I'm not mistaken. It has to do with some French word. So an S-adic sequence, or a limit sequence for a directive sequence of substitutions is a word that can be desubstituted infinitely often. So W is equal to W0, and we can desubstitute. So W0 is sigma 0 of W1, W1 is sigma 1 of W2, and so on and so on. We can write this in a better, easier way. So this is just a formal definition. What it really is, so to say, under reasonable conditions, is written here. So a word is S-adic. Essentially, this is related to primitivity, but essentially it is possible to write it like this. You take a letter A, and you hit this letter A by your sequence of substitutions. You get an infinite word, which is called an S-adic word. Okay? So again, as before, we associate dynamically systems to S-adic words. So we have a shift, which just chops off the first character. The S-adic sequence, for an S-adic sequence, we define the orbit closure of this sequence, call it XW. Then XW equipped with the continuous map sigma is the S-adic shift or S-adic system generated by this word. Okay, so it's this dynamic system generated by the orbit closure. So this XW can be defined in a different way. If you call the set of all finite subwords of a sequence the language of this sequence, then it is just an easy exercise to prove that this orbit closure can be defined as the set of all sequences whose language is a subset of the language of W. This is the same definition. Very often, and we will assume this throughout, the dynamical system, or the set on which the dynamical system is defined doesn't really depend on the word, it just depends on the sequence of substitutions that creates the word. So we will write x sigma instead of xw for the set on which the S-adic system is defined. Again, this is related to some primitivity properties, but you shouldn't care about this. It's just essentially only depending on x sigma. So there is one important case which is very well studied, and many very interesting and beautiful results exist. This is the so-called substitutive case. So we confine ourselves to substitutions where the directive sequence is just a constant sequence. So we just use one single substitution, like in the Fibonacci case, or like in the case studied by Jörg Rauzy in 1992. One single substitution, we iterate it, we get a fixed point, or at least a periodic point, and we cook up our dynamical system, which under reasonable conditions only depends on the sequence and not on the word. So these systems are called substitutive. What is known about these substitutive sequences? There is this fundamental and important result by Rosi from 1982, the role model for everything else, you could say. So he proved that the Fibonacci substitution I defined before gives rise to a rotation on the torus, so there's a measurable conjugacy. Again, the conjugacy cannot be topological. There's a measurable conjugacy between this system and an irrational rotation by a vector which is related to the eigenvectors of the matrix, of the incidence matrix on the two torus. This was considerably generalized by Arnoux. So this list is not exhaustive, I just put some highlights here. There is a generalization of this by Arnoux and Ito, as well as by Ito and Rau. So they showed that a substitutive system is conjugate to a rotation if sigma is a unimodular Pissot substitution, and if on top of that some combinatorial conditions, some kind of coincidence conditions are in force. So what are coincidence conditions? Probably I don't want to go into this, probably later. So these are some combinatorial conditions that have to be satisfied by the substitutions in order to make sure that they are rotations. It is conjectured, and this is the Pissot substitution conjecture, that these conditions are always satisfied. So it is conjectured that a unimodular Pissot substitution always gives rise to a rotation on the two torus. Considerable progress was made by... Ah, sorry, thank you very much. Yeah, TD minus 1 should be here. Thank you very much. A recent breakthrough using the notion of proximality was done based on a paper by Bartsch and Kellendonk. In two papers by Marcy Bartsch, he proved under very general conditions that unimodular Pissot substitutions are conjugate to rotation. So this is state of the art just now. Two papers by Marcy Bartsch from 2016. So Rosi fractals are not boring. So they come up in many different kinds and shapes and topologies. It turns out that the original Rosi fractal of 1982 is homomorphic to a closed disk. So it's topologically very nice. But it's not hard to come up with substitutions that give rise to Rosi fractals with holes. You see here. This one is particularly nice. So the Fibonacci substitution is very famous. So this is this one. Sigma. So 1 goes to 1, 2, 2 goes to 1, 3, and 3 goes to 1. And now you make a slight change. You just flip those two letters here. 2 goes to 3, 1. And this has a dramatic effect. So this changes the Rosi fractal to this one here. So this is not so clear how the topological structures are related to the combinatorial ones. So this is the Rosi fractal for the flipped Fibonacci substitution. The funny thing is, although it looks very complicated, you can do your domain exchange on this. So you can take this one, move it up here, take this, move it here, and take this, move it here. You have your domain exchange, and even better, this is a tile. So this tiles the plane with measure 0 overlaps. It's the closure of its interior, and it tiles the plane with measure 0 overlaps. So the domain exchange can even be made a rotation, and this guy here is conjugate to a rotation. But you see, if you have to prove the Puiseux conjecture, monsters like this have to be tamed. I mean, Marcy-Batch didn't go by the way of Rosi fractals, but essentially you see that something complicated is behind this. Here's another example. I think this has no holes, but you see the Rosi fractals, they don't even have to be connected. So everything can come up. Also, this is nice since it's a tiling, but it's a disconnected tile. Domain exchange, I don't know, but I think the green one is moved here. The blue one is moved here, it's the only possibility, and whatever you do with the pink one, so I don't know, but you can do the domain exchange and the rotation again. So I was talking about the classical continued fraction algorithm. This can be generalized. I first give you the general definition, but probably it's better to understand this by way of an example. So instead of the projective line, we have the projective space now, and we take X to be a decent subset of the projective space, and we partition the projective space by some partition which could be finite or uncountable, and to each element of the partition we associate a matrix. And depending on where we are, depending on where we are in the partition, we associate the matrix to this element. So what does the continued fraction algorithm do? We start with X, and depending on where we are, hits X with a matrix. Like the additive Euclidean algorithm. Also, depending if A is greater than B or A is less than B, it hits the vector AB with different matrices. Okay? And this is just a natural generalization of these concepts to higher dimensions. But as promised, I want to give you an example. The so-called Brun algorithm goes back to 1958, I think, to Viggo Brun, a mathematician from some Nordic country. I don't know which one. Norway. So Norwegian guy. So here's the linear version defined on the projective space. Again, we can projectivize, and we can define it on the half of the unit square. So let's see. What does the Brun algorithm do? So it is fairly easy. So look at this red thing here. The linear Brun algorithm subtracts the second largest element of a sorted vector from the largest one, and then sorts again. So here is our space, B. This is the X from the general definition. The Brun algorithm takes place on B. We have a vector W1, W2, W3, which is sorted. So you take this vector, replace the largest one by the largest minus the second one. You get another vector, and you sort this again so that this series of inequalities is true. Yeah? We are only interested in the case of strict inequalities. Sometimes I'm sloppy and put strict and non-strict, mix them, but we are interested in full measure, so don't care about strictness or non-strictness of inequalities. This is Brun. Subtract the second largest from the largest and sort it. Okay? It's just a natural idea to generalize the additive, classical additive continuous fraction algorithm to dimension 3. So you can write this in terms of matrices, of course. It's not hard to verify it. So you have 3 different matrices. So why do you have 3 different matrices? 3 possibilities can occur. If you sort this could be the largest, could be the second largest, or could be the smallest. That's why you need 3 matrices. Okay? And accordingly, you have to define your regions when you hit the vector with which matrix. So these are the 3 matrices. So you can easily verify this. And the Brun continuous fraction algorithm just chooses one of these matrices if our vector is contained in a region associated with this matrix. So we have a finite family of matrices. Remember, for the classical continuous fraction algorithm, the additive version had two matrices, M1 and M2. The multiplicative version had infinitely many matrices, all the powers of M1 and M2. And in general, if you need only finitely many matrices to define a continuous fraction algorithm, you call it additive. Otherwise, you call it multiplicative. So this guy is additive with three matrices. So it's not really needed. This is just the trace of B, of the region B, and here is how it is subdivided into the three subregions. It's not so important. But it's nice. So S for the classical case. Now we were on the projective space, and now we project on some plane. And it turns out, by easy calculation, that the projectivized additive form of the Brun algorithm is given on a triangle. So here the inequalities are strict, here they're non-strict. I'm sorry for this. Take strict ones everywhere if you want. You just lose measure zero. It is defined in this way. This is a bit more harder to memorize than the linear version, but it's just the same projectivized version of the Brun algorithm. And so now we go the other way around. We don't start with substitutions. We start with the algorithm and we cook up substitutions. So we put a non-abelian overhead on the algorithm. And this is done in this case by the so-called Brun substitutions. There are several different versions of those. I picked this one. These are three substitutions whose incidence matrices are just the matrices M1, M2, and M3. Of course, there is no canonical way to associate substitutions to a continuous vector, to a continuous fraction algorithm. We just choose this one, and we have another system of substitutions that we create S-adic words and that can be studied. So we can define S-adic sequences whose abelianizations perform the Brun algorithm. Those ones are needed to define the Rosi fractals that give the arithmetic and geometric coding of the Weyl chamber flow, for instance. Yeah? So you need to go the deviation over the non-abelian case that gives you some nice objects called non-stationary Markov partitions that can be used in order to code the Weyl chamber flow. So it makes sense to make things more difficult than they are, to make things which are abelian, non-abelian, because it buys you something. So I don't know how much time do I have? 10 minutes. 10 minutes? So I will start a little bit with two easy properties. So we cannot expect unconditional results. We want to impose natural properties on our sequences of substitutions, and some of these properties are better studied on the associated sequences of matrices. So we define some properties of sequences of matrices. First property is primitivity. So we have a sequence of matrices. My matrices are always non-negative integer matrices with determinant 1 and plus minus 1 and invertible. Such a sequence is primitive if you have infinitely many blocks whose products are positive. This is defined here. So we get a primitive matrix now and then. This is important because it entails that the underlying S-adic system is minimal, and I gave you the definition of minimality here for convenience. A dynamical system is minimal if for each point in the system the orbit is dense. Okay? Minimal system means the orbit is dense everywhere. I have some examples here. The standard example is an irrational rotation. So you start with x on the circle of circumference 1, and you rotate by an irrational rotation. So here are 1, 2, 3 rotations. Here are 10 rotations. And it turns out that wherever you start, you will get a dense orbit. So this is the easiest example of a minimal system. Our S-adic systems are minimal if the matrices are primitive. So all the shift orbits of the elements are primitive. A more general example than this is the so-called Kronecker rotation. If you have sufficiently irrational vectors and you rotate on the d-dimensional torus, you get minimality. A counterexample to minimality is the full shift mentioned by Natalie. So you just take all the sequences of 2 letters equipped with the shift. This is not minimal because the sequence consisting only of ones is far away from all the sequences starting with 2, for instance. So this orbit is not dense and we don't have minimality. So what does this lemma say? Essentially, this lemma says primitivity entails minimality for S-adic systems, and also primitivity entails that the minimal system does not depend on the limit word we choose. The S-adic system just depends on the sequence of substitutions, and that's why it is justified under the condition of primitivity that we may use the index sigma instead of the index w for S-adic systems. So they only depend on the directive sequence and not on the limit word created by this sequence. Also, the number of limit words is bounded by the cardinality of the alphabet, and we can be sure that limit words exist. Okay? So this makes our life a little bit easier. We get the first property of our dynamic system, which is minimality. The second thing is recurrence. So why do we need recurrence? Please remember the Perron-Frobenius theorem. So if you take the positive cone of R3 and you hit it with a primitive matrix. A primitive matrix is a matrix which has a positive power. Then you make this positive cone smaller and smaller, and eventually it will approximate one direction, which is the direction of the dominant eigenvector, right? This is the Perron-Frobenius theorem. We want to mimic the Perron-Frobenius theorem. So we don't want only primitivity, we want primitivity and recurrence. We want that the same primitive block occurs infinitely often. Okay, so with one given primitive block, this has to occur infinitely often. And one can prove that such a sequence of matrices acts the same way as the matrices satisfying Perron-Frobenius. In fact, if you take the positive cone and you hit it with the sequence of matrices, the primitive block that occurs infinitely often will make sure that you converge to what is called the generalized right eigenvector. So recurrence just means that every block occurs infinitely often. You can say that an arbitrarily long block at the beginning occurs a second time. This is just obviously equivalent. Here is a lemma of Fürstenberg, the one I just explained. If you take the positive cone, so this is the set of all positive or non-negative vectors, doesn't matter, and you hit it with this sequence of matrices, then this cone will shrink down to a single vector, u. The proof of this is done by a metric on rays in the positive cone. And it turns out that with respect to this metric, primitive matrices are contractions. So you contract the cone, and since you have this primitive matrix infinitely often, the Hilbert metric shrinks down to 0 by a geometric series. Each time you hit this positive cone, you get smaller by some factor c less than 1. Here is a mistake again. Here is a constant missing. So here should be some constant k less than 1, which comes up infinitely often, creates your geometric series, and makes sure that your metric tends to 0, so only one ray survives. And this is the positive eigenvector, the generalized eigenvector. Here's the definition. So if this shrinks down to a single value, we say that the sequence of matrices is weakly convergent. We had this in the Sturmian case. And we call the vector towards this is converging the generalized eigenvector. And here is the remark I already made from the substitutive case. This is just the generalization of Perron-Frobenius. So if your sequence of substitutions is constant, your sequence of matrices is constant. And it turns out if you have a Piso substitution, you always get primitive companion matrices, primitive incidence matrices, so you can use Perron-Frobenius to make sure that the dominant eigenvector always exists in the substitutive case. Okay? So this is a generalization of substitutive case to matrix sequences, and we need some conditions there. Now, here is a definition which is very important. I gave it already before, but now I do it in some detail. So what does unique ergodicity mean? A topological dynamical system on a compact space is said to be uniquely ergodic if there is a unique measure, which is T invariant, and which is a probability measure, okay? So normed in a way that the measure of the whole space is 1. It's a unique measure. So the problem is not the existence, the problem is the uniqueness. The existence is guaranteed by these two guys. So if X is compact, then there exists at least one invariant measure here for convenience. This is the invariant measure. There is one. And so we write here unique ergodicity without ergodicity coming up, but it's not hard to see that if there is a unique measure, it has to be ergodic, because if it was not ergodic, there is an invariant set of measure between 0 and 1 strictly, which can be used to define another measure, which is done here. So a unique ergodic measure has to be ergodic. Unique ergodicity has many nice consequences. One of the important consequences is that the ergodic theorem is not true just everywhere, but it's indeed true everywhere. So if you would have an exception, you could use it to construct another measure. This is how you prove this. So unique ergodicity, there's only one measure. This has to be ergodic, and this entails that this Perkov theorem is true everywhere. So it turns out, can I have 2 minutes?
Yes.
2 minutes? So shall I do it? I do it next time. I think I do it next time. I don't want to overcharge you. You have to listen to a very long time during the day. So I will go on with consequences of unique ergodicity with the conditions that are needed for unique ergodicity tomorrow. So thank you very much for your attention. Thank you.
Okay, so today is a special day because you are recorded. So if you have questions, please ask for the microphone. And your question will stay forever in the memory of the CIRM. For the answer too. Okay, so do you have questions? For the moment, the microphone doesn't work, so you can ask your question in class.
So am I right that all Arnoux sequences are not mixing, not strongly mixing? So they could be weakly mixing,
yes, yes.
They cannot be strongly mixing. Is it right?
I don't know. So there are no results in this regard. Let me think a little bit if there's some reason why there couldn't possibly be.
Did Pierre and Gerard prove that they all can be given by 6 interval exchanges? Or then it follows by Katok's result that interval exchanges cannot be mixed.
Okay, then it's okay. Then it's okay. Yes, yes, yes.
Is there a way to make a simultaneous diophantine approximation of several points at the same time in the two-dimensional torus? I am thinking about the symmetric power of the torus by itself n time in this space. It could be some kind of diophantine approximation. If you don't like this space because it's singular, you can take the Hilbert scheme of n point, and that is smooth. So my question is there some kind of work to approximate endpoint at the same time?
Yes, there is a kind of way to approximate endpoints at the same time. For instance, if you look at the Fibonacci substitution, this gives you a best approximation of the vector related to this point.
But this is one-dimensional. I said that the Fibonacci substitution three times in the same two-dimensional torus. For example, 3 points. Each point have 2 coordinates, so you need to approximate 6 numbers at the same time. The 3 points at the same time, not just one vector of point.
So you want to approximate 2 3-dimensional vectors at the same time?
Yes.
This is you want to approximate a 6-dimensional vector?
Yes, yes. In order to obtain a space, a configuration space of point in the torus that is an object well studied in algebraic geometry, the space configuration of point of a torus. there are many results about the cohomology of this space, and it is related to number theory by means of veil conjecture. The Hilbert scheme of the torus is very important, and I think that simultaneous approximation of vectors could be done in the Hilbert scheme, maybe.
So this I do not know. So what we can do is we can approximate one given vector by means of multidimensional continued fraction algorithms. But for several vectors at once, I don't know.
Okay, maybe a last question. No, so I have just a short question, maybe. You define the Sturmian ones, not only you, but by the complexity. Then the Arnoux Rauzy sequence by the complexity. And then you doesn't talk anymore about complexity. Is there some definition of the broken line, for example, for Fibonacci as a minimal complexity among some class of words?
So, in fact, it would be interesting to know if complexity questions are related to the existence of nice Rosi fractals. But so far in our theory, we did not encounter any relation for complexity. What is important for us is just that we have this S-adic representation, which gives us a sequence of matrices. And then we need to make sure that this sequence of matrices has decent properties. To what extent they are related to complexity, I did not explore, but this would be certainly interesting to get some characterization in terms of complexity of these.
Maybe among the broken line which stay at a bounded distance from the line they approximate, or?
It's balanced, so the natural property here is balance. It's even equivalent. So if your sequence is balanced, it stays at bounded distance.
Yes, but for example, BR words, they are worse than Fibonacci words, no?
Yeah, but I mean, we always need S-adicity, of course. Mm-hmm. So S-adicity is needed to play our game. We need primitivity and recurrence to get the weak convergence. And then we need balance and some other algebraicity property to get strong convergence, which entails that the Rosi fractal is bounded and can be subdivided into pieces whose diameters converge to zero. These are the important things for us. I never saw how linear complexity would show up in this context. But it's certainly worth looking at this, what kind of complexity can come up. But it is not so easy. So for instance, if you look at the Brun continuous fraction algorithm, there are two people here, Julien Leroy and Sébastien Labbé, who work very hard to prove that they have linear complexity. And also they are, I think, in some final stage of their proofs. Is that true? More or less, it is still not clear, even in this simple class, if the complexity is linear or not. It's quite tricky, and I think it's a many pages paper that will come up. So, but it seems, for our theory, it seems to be not related. Also, it would be very interesting, and in this context, also the new algorithm by Julien Cassaigne is of importance. So, if those two people succeed in proving linear complexity of the Brun sequences, then by our theory it follows that for almost all torus rotations on the two-dimensional torus, we have a partition that gives rise to a coding of linear complexity, which would be a nice result, because as far as I know, the codings that are known so far always have quadratic complexity. So it's interesting, of course, but it's difficult, and we don't need it for our arguments, although it would have nice consequences.
Okay, so let's thank the speaker again.